Ready to go? Yeah. Okay, welcome to our weather discussion. For today we have a triumvirate of interest. Today I'll talk a little bit about the current weather and a recap of the winter in just a short bit. Then Patrick will talk about the forecast, and then Andrea will talk about, I think it's an extended forecast of the end of the polar stratospheric vortex or of the warming event, or both.
A little bit of everything.
Okay,
yeah.
It'll be
All
awesome.
of the above.
I'm looking forward to it, so that'll be excellent. Here's the 850 cold pool for December, January, February of 22-23. So it's now complete as it ended on Tuesday, I guess. And it turns out this is the 16th warmest December, January, February since 1948-49. So it hung in, it was always somewhere in the 10th to the 15th-ish range all winter long. And so we never really had any exciting prospects of getting much colder or exciting prospects of getting toward record warmth. But it looks like, to me, like the hemisphere was about a little below average in December, well below average in January, and then about average again or a little below in February. So that puts us 16th on a list of 75 winters now, or 74 winters. So, you know, that's about all you can say about that. The last week or so of February was a rapid reduction in the amount of cold air at 850 millibars. I don't know if it's likely to undergo another increase. I do have records for the subsequent months, but I don't often look at them, so I might do that this year. So that's the first piece of interest about this past December, January, February. You might recall that I have a long-term time series where I take the average of each of these 90 days and compare that average against the long-term average every of the 90 days. So you can get a seasonal December, January, February average as well. And this year it ends up at about 66.9 million square kilometers is the average aerial extent throughout this winter. And this puts it in the context, the top line, puts it in the context of all of the years from the NCEP reanalysis back to 1948. And I didn't readjust my trend line, and the dot showed up just about right on it. So it's just a systematic trend. And you can notice, though, that there's variability interannually, but there's no changing of the trend. I mean, it's really a marked trend downward. In 1948, the average area for the whole 90 days was 70 million square kilometers. Now it's not yet 67. So that's about a 4.5% decrease. And that's a substantial decrease, as it turns out, when it comes to the atmosphere. And then all the other threshold values, I could extend as well. I have data for minus 10 all the way to minus 25. And they all have roughly the same trend line. It's a little steeper for the colder ones, for the warmer ones, and not quite as steep for the colder ones. But that's because you're getting vanishingly close to zero, I think. You know, eventually they may be zero, minus 25 air. It's going to be a long time from now, but that might happen someday. But there's a long-term trend that's significant at the 99.9% level. And every year when you put a new dot on there, it just falls right in line. So kind of insignificant. It's getting warmer. Yeah.
What does the interseasonal variability look like? Are cold years less variable than warm years?
That is very interesting. So, for instance, this year, is this a cold year? This is a cold average year. Is it, so would the time series have more variability?
Right.
It doesn't seem to correspond. Because I looked at something that I measured with standard deviations as the volatility, inspired by some discussion I saw on a business channel one day. So you look at the time series of the Dow Jones Index, they can talk about volatility. And it really comes down to what's the standard deviation across the whole thing. And so this would have been a pretty volatile year with only one giant growth period, maybe two, and one that was fairly stagnant. But some years, it's just one giant growth to about early February and then a decay. And so the answer that I think I have looked at, not including this year, is that there does not seem to be a connection, but an excellent question. And I don't know, though, about the circulations in the hemisphere, whether or not they have some kind of correspondence to the particularly cold years that stand out. And you can see there's decades where there's a preponderance of colder years than the long-term trend, and then maybe even decades where there are years that are quite a bit lower than that. One thing that I think is still true is that you never get a streak of more than 1, 2, 3 years of increase or 3 years of decrease, which is really sort of weird. I mean, why should that be the case? But it seems to be the case. So, very good question, Andrea. I don't know the answer. I think there's a lot. NSF's never going to fund more investigation of this because I can't even articulate what the questions are. But I think when I'm retired, I might have a lot of fun playing with this data because I can do it at no expense to them. Here's something else, though, that's entered my mind a little bit more. I've kept track of it for a long time, but I've not really thought about it much until now. This is the same annual average for 1948, September, October, November average together, and then going all the way to this last year for September, October, November, and then December, January, February. So these are the predecessor months to the actual winter. And at first glance, it's not surprising, of course, the autumn has an average that is much lower than the average in the wintertime. Although at the end of the autumn, those values are kind of close to, the beginning value, well, it's exactly the same as the beginning values for the winter. So they get separated just because the average is over such a long period of time. But what struck me is that they don't have exactly the same time series. In fact, if you put them on top of each other, sort of just do that on purpose, the correlation's only 0.575. And sometimes you can notice long periods of time where they don't seem to have any relationship to each other at all. Although the broad trends in both are identical, which is quite interesting. So there's something about the fall and the winter that they're connected in terms of the long-term trend as a diagnosis for what's going on Earth broadly. But a given year in the fall has almost nothing to say about what you ought to expect in the wintertime. And in fact, if you think about taking all of the fall years, ranking them from the warmest to the coldest, and so warmest would mean smallest areal extent on average, coldest would be biggest, and do the same with the wintertime, you can talk about a rank list change. And Patrick came in and made me aware that I've not made a good explanation of this. So you can rank all your September, October, Novembers. The warmest one will have a rank of 1, coldest will have a rank of 74. Then you rank your December, January, and Februarys, and you do the same thing. And then look at each individual cold season and see what was the change in rank from the fall to the winter. So if you have a negative change, that means you got colder in the winter. So we were 16th warmest winter, but we were 8th warmest September, October, November. So we lost 8 places on the rank list for 2022-23. And then the reds are years where it got warmer in the winter, so that the fall would have kind of pointed you in the wrong direction, and you get warmer in the winter. Most of these years, let me just see. First of all, I'll just tell you the stats. There's 75 years, 37 of them have gotten warmer gotten colder in the winter, and 38 have gotten warmer in the winter. So they're almost exactly split in that thing. Of the 37 that got colder, the blue ones, only 12 of those 37 have had as minor a rank list change as we just encountered. Anything 8 or smaller has only happened 12 times out of those 37. So it's more unusual than not if you get colder in the winter, to just get incrementally colder by the rank list change. And look at some of these years, like 2011. You switched places by more than 50 places on the rank list from the fall to the winter. The fall was much warmer than the subsequent winter. And what I think this means to me, and there's big spikes most of the time, it's more than that. I think this means that you can't use the fall to make any prediction at all about the winter. There's just nothing there. And so that's one of the reasons why this runs into the ground in terms of NSF. They're going to say that right away. There's nothing to learn here, except this is still a statement you can now say with confidence. I think that's fair to say. And I'm still interested about looking at individual years. What happened to the global circulation when the polar stratospheric vortex was set up in that fall? Because everything changed in the wintertime. How come? And then similarly, you could go to the highest ranking warmer winter, which was 1986. How come we got almost a 40-place rank change? And we have 5 of them that are almost that high, 4 of them that are almost that high. This one stands out all by itself, almost all by itself. So I'm intrigued about looking at individual years, but there's nothing to be learned about predictability, I don't think, on the grand scale in this case.
Also interesting, the long periods of the same sign too. You got the
a lot
of, like 8 in a row that were less.
Yeah,
like 5 in a row that were more, and there are some long periods in there too.
Yeah, and these two here, it might just be the, I don't know, something about the immaturity of the NSF reanalysis. It's possible. But when you get past about 1960, because the JRA is 1958, I have a little bit more confidence that something really honest is being recorded here. And it does seem a little funny that this is the case.
You got it in the 2000s and 2010s too, though, right?
Yeah. That's a long
bunch of warm
period,
ones
that's right.
followed by a bunch of cold ones.
And this is centered around or close to a period where there was a prolonged, historically negative NAO. So there's things like that that kind of pique your interest. You want to know whether or not there's something to it. But I think there probably isn't, except for investigating the individual years, which could be kind of fun. Okay, so that's all I have about the cold pool. And so, can we go back to the, what do I do, Pete? Go to the,
Room PC,
okay.
and then move the mouse if it's, yeah. Andrea's got a bunch of stuff loaded up.
Oh,
All the
okay.
tabs.
You
all
can
right.
just go to our, or wherever you want to go.
Yeah, I'll just go to AOS.
That's, if just hit enter, it's got it.
Oh, it does?
Yep.
Okay, all right, that's great. Okay, so let's start with, other watch things. So,
Do you want me to drive with that, John? Or?
yeah, because I just, I'm not familiar with driving from this page and it'll waste everybody's time. So let's start with the 6-hour satellite image over the continental US. So every year, I hope that we get the warmest winter ever, or one of the coldest winters. Oh, the other thing I should say, one last thing, we still have not had a 2 sigma cold event. And that last one that happened was February 12th and 13th of 1994. So next year, if we don't get one, we will have had 30 straight winters without a 2 sigma cold event, which is, what I mean is a cold aerial extent, so a large extent that's twice the standard deviation above the daily calendar mean for that day. So we haven't had one. They don't happen anymore. And I picked that arbitrarily in 2014 as the cutoff for the paper, but they just don't happen anymore. Look at this beautiful set of storms in the North Atlantic and over the continental US. This one yesterday, I'm not going to say more about it than this, but this complex of 2 storms ended up making this one, for the first time I've ever seen, have couplets of upward and downward vertical motion that rotated past 12 and 6 o'clock. They kept on going. I've never seen that before. But that was because, and it's gone today, but that was because they were caught in a much broader cyclonic circulation. But a really intense storm at the southern part of the Labrador Sea, beautiful cold frontal cloud mass, probably occluded frontal boundary in there. And then this is the next one south of Newfoundland. Very intense, again, big cloud head. And then we've got one developing just to our south. Looks even better in the infrared in terms of finding the circulation center, but it's over southern Illinois. And we've been in the clouds and murk all day, all night last night. Wednesday night, I got off the bus and I saw the conjunction of Jupiter and Venus. Did you happen to see that? And it disappeared in the next 20 minutes. I got off the bus about 6:30, brought my wife out to look at it. I wondered what it was, looked it up, what's going on. First time in like a year or 10 months or something. It's not that long ago. It won't happen again for 13 though. And then went back out again to get another look, and the clouds had come in. And those were the clouds with this advancing system. So it's taken its time to get developed. But it's rapidly developing this morning, so we can take a look at elements of that. So 3 really major extratropical systems in this portion of the satellite image, and then not so well organized anywhere else in the western half of the United States, and then into the immediate waters off the Pacific. But these are beautiful storms, and this conjunction of these two, or near approach of these two, really played some funny games with the vertical motion distribution in a way that I've not seen before, and maybe it takes this kind of an interaction for that to occur. Okay, so let's take a look, Pete, if we could, at the, can we just take a look at the infrared? I think you can just peer through a little bit of that, not this one, the black and white.
Let's see, we have to actually go to the webpage.
Oh. Yeah, you can see through a little bit of this lower cloud. You see that it is lower cloud. It looks a little more ominous in the visible, but you can see the center of the circulation there in southern Illinois really nicely. This blossoming convective line is got, SPC's got its eye on that again today. I think they had tornadoes in Arkansas yesterday, and there were some in Tennessee. So it's been a pretty tough week for portions of the southeast United States already, and this storm is packing a pretty good punch right now in some of those same places. Okay, can we go to the radar, the national radar? Yeah, really nice radar summary. Look at the slow creep northward of the northwest and northern edge of this cloud. It's maybe going to start to precipitate soon in Chicago. Maybe it won't even quite get there. I don't think it's going to get to Madison because this is all translating also to the east as it does so. But here's a line of really intense convection. We just saw that blow up in the satellite movie. Look at how narrow that is through northern Alabama. So Birmingham and then places north and east of there are in trouble. Nashville the same, so that's going to be interesting. And then western Kentucky has a second line right in there. And so heavy precipitation in, I guess, the Springfield, Missouri area, same in St. Louis metro area. And so it's going to be an impactful storm. but really beautiful illustration of the comma cloud nature of these things. Sometimes you see it in the clouds and it doesn't show up so nicely in the radar, but it does in this case. Beautiful extended warm frontal type precipitation band. Obviously the cold front with a squall line along it, and then this interesting, perhaps post-frontal squall line in western Kentucky, and then some precipitation that's wrapped around to the northwest. It's actually generated there. I hate that term, but it works because people have heard it before. But this is actually generated there, and of course the question is, what's the dynamics that drives that? And that's always of interest. I think it's the vortex cyclogenetic vertical motion from my past work. I don't know if that's the case today. So this is roughly 18Z. We'll be able to look at that in a minute. That'll be straddling the St. Louis metro area where the vertical motions might be. So we'll see in a minute. And then some open cellular convection coming onshore in the Puget Sound. It's another one of these kind of cold core upper disturbances. Maybe not as dramatic as the one last week that came all the way down to Santa Barbara from Southern California and dropped snow in some places that don't usually get it. And then some places don't usually get 8 feet of snow, like Yosemite, which is closed. So pretty amazing last several days. Portland, Oregon got 2 major snowstorms. Seattle got a fairly major one for them. I mean, they sometimes can get 6 inches of snow. I don't know if they did this week. But Portland bore the brunt, and then so did the southern part of the state, especially the higher elevations down there. So really interesting. Okay, can we take a look at some of the upper level charts, Pete? And of course, the super Pete's will do. We'll start at 500 millibars. So here's 12Z this morning. It's Friday. Pete's out of the days for me. That's really helpful. This is a really sharp upper trough. It doesn't have very much longitudinal extent. Sometimes that's helpful, sometimes it's not. I think in this case it's not. It's more of a narrow trough feature. And as a consequence, I suspect the vertical motions will be rather concentrated around its position. So ascent about here and descent back this way. A little bit of a ridge downstream. Not much thermal contrast left at 500 millibars except right across the Dallas-Fort Worth area. I think it's minus, I'm going to say that's minus 20 at Dallas, and it's something on the order in the single digits below 0. It's just south of there in Texas. So a very strong middle tropospheric baroclinic zone, but of narrow, limited horizontal extent. Probably means it's a fairly small upper level vortex structure. We'll take a look in just a minute. And that will limit the ability of the advection of that vorticity to change the divergence profile and produce vertical motions of really strong consequence. Contrast that with this upper wave, which has considerably lengthier and maybe a little bit better organized baroclinicity at 500 millibars. And so we had one cyclone off of the maritime provinces. The second one is south of Greenland that we saw, and that's also got a really sharply curved, oddly oriented but sharply curved upper structure to it. So one of the things that characterizes both of these is that the waves have either a neutral or a negative tilt. And that accounts for their really nicely occluded structures. This one has just barely a negative tilt, but neutral will do as well. Downstream ridge allows for some wrapping back of the cyclonic circulation in the lower troposphere. A couple of storms we've seen earlier this year have not really had that, and they've not been able to occlude. Like the one, was it 10 days ago or last week in Minneapolis? There was just no chance that was going to occlude, and I made a comment about that last week. And the consequence was certainly less snow in the northwest side of that storm than one would expect to get in the northwest side of this one or the northwest side of this one. Can we go to, let's go down to the 850 level first, then we'll go up. So at 850, storm 1, storm 2, really interesting thermal structures, kind of a little bit of an occluded thermal ridge there. This one's got just a warm core now. It's kind of really wrapped itself up, but I suspect this was the old thermal ridge for the occlusion in here, plus 4 degrees. We're going to plus 4 degrees at 850 just south of the southern tip of Greenland. And we're at minus 1 at Green Bay. Somehow seems a little bit unfair. Here's the cyclone over in northeast Arkansas, and it's just about exactly downstream of that sharp upper trough. So that's in the right place. But I think it will struggle to continue to develop, not translate, but develop, because that upper trough really doesn't have as much oomph to it, apparently, as others, of its nature sometimes do. And but you look at that baroclinicity, even at 850, where it might get disturbed in the Appalachians, you can see a decent temperature contrast here. It's plus 4 at Lincoln. It's plus 11 in Nashville, plus 14 in Birmingham, plus 14 at Jackson, so very warm and very moist too. The dew point depression is only 4. It's even lower than that in New Orleans, while warmer. So this is warm, moist air, and it's coming up over colder and much drier air. Look at the dew point depression at Lincoln's 22. So this is an entirely different air mass, poleward of that baroclinicity at 850, and it's confined within a region where there's strong frontogenetic forcing. So no surprise that we see the radar reflectivity stretched all the way across to the East Coast. And part of that is the cold front of this old storm. So they're not unconnected. And one can see that there's dynamics that connect them there as well at the junction point, like over Virginia. So the question in the forecast is what's the future of this event, and what's the future of the baroclinicity over the northeastern U.S., and Patrick will tell us a little bit about that. Can we see the 300 millibar map? So at 300 millibars, we have a really strong jet associated with the kind of broader and broader trough. The higher up one goes, it's a fairly sharp 850 millibar geopotential minimum. It's a little bit sharper, 500 millibar trough, than here it is at 300. It's much broader. But the jet is on the western side of this broad trough, and that tends to mean you get pretty decent cyclogenesis right in here. You get the benefit of being downstream of the curvature maxima, and you're in the left exit region of this jet as it's oriented currently. And that's a pretty good region for vertical motions. And that's where the thing is really wrapping up, right there off the maritime, coast of Newfoundland. This storm has a little bit weaker 300 millibar signature, but it's relatively warm, so the tropopause is really low, well below 300 millibars there. So that's interesting. And then I mentioned the open cellular convection coming in off the Pacific coast into the Puget Sound area, not unrelated to the fact that there's yet again another cold trough off the coast of the in the northeastern Pacific Ocean. So this one doesn't seem to have the legs that the one last weekend had that could dig well south and really make it cold along the entire coast. But it is colder than it normally is, all the way through the troposphere off the coast of British Columbia and probably Washington State, maybe not all the way down to Oregon. And that's likely to be exacerbated because of the curvature being out to the west with the jet maximum right at the base. I think that trough will dig a little bit as it moves to the east, so they'll probably stay cold in Seattle and stay showery, maybe mixed rain and snow. I don't know what the surface temperature there is right now. And then finally, our storm that was over Arkansas, the one of interest for us, because we're on the northern periphery of its clouds, stubby little jet. Not so bad if you have a stubby jet, because you have strong gradients of a long flow speed change, and then coincident with the curvature. So the maximum ascent is down here in southeastern or southern Missouri more broadly, just about right where we saw the maximum reflectivity on the western side of the storm. In fact, that reflectivity is hours after this, so it's probably connected with that exact thing, now that I think of it. So lots of things going on in the weather today, and some of them are gigantic, cyclone scale, and some of them, though they're producing cyclones, on a smaller scale. It just proves that, or reminds one, that these processes are ubiquitous and are flexible. They can do a lot of work with a lot of different broad-scale environments within which they do that work.
So, John,
Yeah.
along those contexts,
Yeah.
thinking about even larger scales,
Yeah.
just basically in the maritime northern parts of Canada, we have southerly flow at 300.
Oh, that's right. Look at this.
And,
1, 2, 3.
Yeah, and we have easterly flow sort of over, in that region.
Yeah.
And thinking about large scale, I might, if I have time, show some maps sort of the hemispheric flow. And this is setting the stage for potential cold air going into Europe,
Oh.
so not quite cross-polar, but really high latitude.
Cross high latitude.
Over this ridge downstream.
Wow, interesting.
So, yeah.
And this ridge is certainly being pumped up by storm number 1 that we saw in
Yeah,
Greenland.
and
And
then
this
storm
one here
number
is
2.
going to find its way in
Yeah.
there too, I think in the forecast. Wow, that's really interesting. And I don't know whether or not, I didn't go far enough myself earlier this week to see whether or not this thing contributes to any more of that. But it did look like there was a big block that might build over Western Europe. Maybe somewhat transitory, but that's really interesting. I would never have looked at that. I'm so glad you did.
Yeah. So-
That's really interesting.
In the aftermath of substratospheric formings, the Greenland block is usually one of the signatures. And so this flow sets up, and that's why
interesting.
Eastern Europe, sort of sometimes Western Europe,
Yeah.
gets colder outbreaks.
Wow, that's really interesting. And Seraphin Hauser's working on these weather regimes, over North America now, like the Karlsruhe group has done over Europe, and so this must be one of them. I don't know that it is or isn't, but I bet you it is.
Yeah.
That's really interesting. Well, okay, I think that's it for me. I don't have anything else to say. I guess, could we look at the SPC page quickly? I want to see what they're talking about for threats today. Okay, yeah, so the threats seem to be following that cyclone, and that's not surprising. Static threat. Oh, there it is. So enhanced threat, remember our cyclone at the current time is over northeastern Arkansas, so it's in this warm sector area. South, predominantly south of the warm front, which is roughly like this. Because remember St. Louis was 40, I think it's true in the middle Atlantic, and then suddenly it's 70 in these locations. So this is the place, Tennessee and Kentucky, where you're gonna have to worry about some really, maybe potentially dangerous weather coming up this afternoon and evening. So that's it, yeah, Charlotte, Cincinnati, Louisville to Lexington and Knoxville, and then a broader slight risk outside of that. So not unexpected, but nice to know that it's consistent with everything we've seen. So I think that's all I have. I would show you the vertical motion stuff, but it's just redundant on everything else we've already said, so you can look at it on your own if you're interested. Patrick? Sure. Thank you, Pete.
You're welcome.
Could we go to first the surface map really quick? I'll keep this brief because I'm also interested in what you have to say. Could we zoom in on where this low is located? Right over southern Illinois here. Okay, so earlier there was at Paducah, Kentucky, right here, there was southerly flow and it was 69. This station in Missouri was northerly flow at 49. So there, the center of the low was sitting right over Paducah, Illinois, and Kentucky. Lowest pressures ever recorded in this region of the United States.
Oh, is that right?
Yeah.
Wow.
So this is 978.8. These are all record low pressures associated with that storm. So I just wanted to point out because that's something very noteworthy.
Absolutely.
And then could we go to the 500 hectopascal loop from our page, please? Sorry, the forecast. So there's 3 precipitation events potentially for our region. If we could stop and go to the start. We'll go 2 clicks, so we're at the current time. So here's our low, centered over about the same location as it is at the surface. And we can watch if we just click forward, we'll see it progress slowly towards the northeast, and we lose that sharp gradient in vorticity advection and potential PVA by the thermal wind as it moves. If we keep clicking here, and the vorticity just becomes diffuse and we lose a clear circulation as it tracks over the northeast. But on its tail, if we go back just 2 clicks, we see a little shortwave feature begin to move over our region. So on, this is Saturday evening, we have the potential for light snow. And I'll show that it is cold enough for this to be snow over our area and areas to our north. Then if we just keep clicking here, we'll see our next potential weather maker. Very deep trough over the western United States. It just continues to dig over this loop. If we just keep clicking, we have maybe another, sorry, I missed this one. If we could go back real quick. Here's another little shortwave that moves off the Rockies. If we click forward, we are in the same region of downstream vertical motion as like the event over the weekend. So this might also be another weather maker. It looks like this one will be rain for us, and I'll show that. How I made that conclusion, but then we still see this very broad and deep trough over the western United States. And towards the end of the week here, this thing, we finally have some disturbance that moves all of this energy over the western half of the United States. If we keep going towards the end of the week, now we're into Thursday morning. We can keep clicking here. Thursday afternoon. Now all of this energy and vorticity gets ejected over the mountains, and we might have a potential large weather maker for the, we can go back to the last image, for all of the middle of the country. And this might be a snowmaker for areas to our south. It might shift and be a snowmaker for us, but this is something to watch towards the end of the week. This is Saturday morning, the time we're looking at. So we'll look at the same view and we'll go to the surface now, please. And this will be the last thing I touch on.
remarkably persistent, one time after another, this long filamentary vorticity structures off the west coast in the last 2.5 weeks.
That's right. We've
Really
seen this
incredible.
picture happen over again. So here's the low and the associated precipitation. If we can keep clicking here, we'll see it move off over the Northeast Pacific and lose its structure and its heavy precipitation. Here's if we go back 2 or 3 clicks, here's our little blip and associated with that shortwave. So this is maybe very light precipitation, but there is a signal for us to get precipitation. The 540 line is well to our south, so this might be snow for us, very light, but indeed snow. And if we could keep going, we'll go to Monday now. We'll see another disturbance move off the Rockies, and here's now the 540 line is to our north here in Madison, but areas to our north might get heavy snow and we'll be stuck in the rain again, as was the case for last Monday. And then if we keep going through this loop, we'll see this system exit. We get precipitation for about a day, and then we move into cold air advection in its wake. And if we keep going, we can just keep clicking P. We'll watch, here's the next weather maker moving over the western United States.
It's maybe more snow for Seattle, Portland, or the coast.
Exactly.
Again, amazing.
Exactly, yep. And right now, they probably don't need this snow. They've had, the basins are 200 to 300% of their normal for snow water equivalent. So this feature, and if you keep clicking, we'll watch it just kind of linger and keep forcing precipitation over the western United States. So this is a bad signal, slowly becoming a bad signal where precipitation early on was good because they were at a deficit. And then here, let's just go to Friday afternoon. Here's potentially the next weather maker for much of the central United States and into the southeast here. And so that's all I have. Are there any questions about what I showed? I know it was brief.
Yeah, man, that's going to be something.
Perfect.
All right, well, actually, we can leave it here to sort of do the transition. All right, so what I want to talk about is the extended forecast. So really looking beyond just next week out into week 2 and maybe 3. And so the way that I want to do this is sort of give you a little bit of background on what's going on in the stratosphere, the disruption to the polar vortex, and what implications that has on our weather. So I wanted to leave it here because it's a really good example of sort of looking at the series of weather systems that we are going to experience. But also if you look at this, we see there's a series of cyclones off in the Atlantic, and if you kind of squint your eyes over the last couple steps through the forecast, you notice that this is just a big blob of low pressure over the last couple forecast steps. If you look into the high latitudes, Greenland, even high latitude Canada, we have, I could see it better from far away, but there was like a 1055 high here that was pretty persistent for a while, almost 1060.
1057.
Yeah, so this high, if you look at it, it's really a large feature taking up most of continental North America. And then if you sort of look outside of the high latitudes, we see lower pressure and lower pressure. So this isn't a climatological feature. This is definitely a feature. It's been persistent for basically the last week of this forecast, but it's a feature that is common after the disruption of the polar vortex, over the high latitude regions, and this sort of extended trophiness, low pressure over the North Atlantic. After a disruption in the stratospheric polar vortex, typically we see the North Atlantic storm track shift a little bit further south, but also sometimes, in certain cases, we get a more active entrance region to the storm track. So that's where I want to go with that. And also, okay, yes, it's great we have high pressure over the high latitudes, but if you think about what goes along with high pressure in the wintertime, usually that's cold air. And so if you look at some of these this is the 510 line, sort of reaching the US-Canada border. So what I want to do now, and I can drive Pete, because I don't know where all my tabs are.
Okay.
So I just wanted to look here. This is the CPC's temperature outlook for the next 6 to 10 days. Basically cold over a lot of the US, and actually if we go even, I think if we go to 8 to 14 days, so basically this is week 2, cold. So, this isn't something we see frequently, but if you actually go to their discussion, the key messages here, updated yesterday, here's their big key messages. the outlooks, and they go into some, sub-freezing temperatures, blah, blah, blah. And then they go down here and they talk about why there's higher than normal confidence in this pattern change as a result of favorable circulation patterns, both from the tropics and the Arctic. So the tropics, I'm not going to talk about this right now because that's what I didn't prepare, but there is a record-breaking MJO convection event in the forecast in phase 8. And what that can do is be a Rossby wave source. So we have this big boom outburst of diabatic heating in a certain location that can force some Rossby waves downstream. Teleconnections tell us that it can impact the US. And 2, an ongoing sudden stratospheric warming event that can lead to cold air outbreaks. And so really this is the part that I'm going to focus on, but just know in the background that the tropics are also having an impact on what's going on. Okay, so in terms of what is happening in the stratosphere, there's some good explainers out there, but essentially we're thinking about the stratospheric polar vortex. So we're thinking about things that are happening well above our heads, 10 to 30 miles. Usually we think about the polar vortex and we measure whether or not a sudden stratospheric warming happens based on a threshold at the 10 hectopascal level, which is about 30 kilometers. And what we're looking for is, we're looking at the circulation around the stratospheric polar vortex. And when we think about the circulation, we're thinking about the stratospheric polar night jet. And if you think about a jet, we know that the thermal wind relationship is part of the description of a jet in our atmosphere, especially in the high latitudes. So we have the cold air inside the vortex and the relatively warmer air on the outside. So when we have a stable stratospheric vortex, the cold air is generally constrained in the high latitudes. And when we have a disrupted polar vortex, the cold air is less constrained. We have a lot more high amplitude flow. The circumpolar winds around the vortex are weaker, and we call it a sudden stratospheric warming event when those circumpolar winds actually, in the zonal mean sense, reverse to easterly. So we can actually look at that. Let's see if is it this one? No, it's not that one. Where is it? I have a tab here that has a good, this one. So what this is from the ERA 5 data. It's looking at the climate from 1979 to 2021, but we're looking at the 10 hectopascal zonal mean winds at 60 degrees north. What is that? We just travel along 60 degrees north latitude and average the winds at every location around that latitude. We get one value, and this is what they do over the course of September to May. So at 10 hectopascals, the winds are pretty much close to zero in September. As we head into the winter and that cold pole develops in the stratosphere, winds increase. And also, if you think back to, maybe your second semester dynamics class in undergrad, and I know this because I taught it for a lot of years, you learn about circulation, and it's just the closed integral of v dotted with some displacement vector. That's essentially what this is. The displacement around 60 degrees north doesn't change. Only the wind changes. So what you're looking at is the circulation over the northern hemisphere in the stratosphere. So we have an increase climatologically that peaks in late December, right around the solstice, and then it decreases as we head into spring, and usually the transition from westerly winds to easterly winds in the stratosphere happens mid-April. But if you look at this, this is the variability with the max and min in this climatological period. There's not a lot of variability in the spin-up, but there's a lot of variability in the breakdown in the vortex. So if we look at what's going on right now, let me go to 10 hectopascals. So NASA maintains these pages, and you can look at, so this is now going for the full annual cycle, so it sort of looks a little bit different. Black line is CLIMO. The blue line is last year's variability. The red line is this year, and then we have analysis data before it went into the Mirror 2 reanalysis in purple, and then this little sort of brown, maybe gem pet color, what is that, 18? That brown color that nobody likes?
I would have thought it was 9, but you know
Oh
better
yeah,
than me.
I don't know. It's been a long time since I was gem pet. But if we look at this, there was a sudden stratospheric warming event that happened February 16th. There's been easterly winds. There was a little blip back up to westerly, but we're in easterly again, and they're expected to stay easterly up until next week. So, let's see, I have about 5 minutes left. So what I wanted to show you, what is going on here?
You zoomed in on that, I think. earlier.
Yeah. Let's see.
Oh, weird. Try to zoom in more. You get more of it when you just get zoom
Yeah.
bigger.
I just refresh the page. Maybe? No? Well, this was going to be a really great animation.
Zoom in more. I think that we're seeing more of it if you zoomed in more.
Zoom in? Okay. Oh, there we
Oh.
go. Okay, I won't zoom in. Reset.
It was there for a minute.
Yeah. All right, well, we'll skip this one. We'll go to this one. Okay, so what you're looking at here, the other one was an animation of the potential vorticity at 10 hectopascals, and you can see the breakdown of the vortex. But this one is close enough. So what you're looking at here is from February 17th GFS forecast. We're looking at the forecast of the geopotential height at 10 hectopascals in white, and then the temperature at 10 hectopascals is the color fill. And already, this is a day after the sudden stratospheric warming happened. And what you can see is that the typical vortex is displaced, and the US is here at the 9 o'clock. Sort of, this is the 0 longitude contour at 6. So yeah, Europe is right here. So the polar vortex at 10 hectopascals was displaced towards Europe, and we have a very amplified high. If you look at this, this is a wave number 1 pattern for the northern hemisphere. There's one trough, one ridge. So this is definitely huge planetary scale features that we're talking about. And as we step forward, you can see that there's a lot of, the vortex wobbles around, gets disrupted, but in the forecast from the 17th of February, the disruption stays, and there's actually an anticyclone that sort of takes over at 10 hectopascals. Looking at time, we don't have a lot of time. So what I wanted to show you here is,
Keep going, Andrea. It's informal. People can leave.
okay, so what I want to show you is, this is a forecast from today. And so we're looking at the GFS forecast. And this is a forecast for the 10 hectopascal zonal mean winds. And there's forecasts, I'm forgetting, oh yeah, here's the forecast. So it's the NASA model, the GFS ensembles, the Canadian model. I forget who this is.
Is that the Navy?
I think it's a
Fleet
Navy.
numerical, I think.
Yes, you're right. But all of them basically are pretty good in under, you know, their alignment where there's going to be some recovery eventually out near basically after next weekend. So we're going to have easterly winds in the stratosphere. That we're having a reverse circulation in the stratosphere for an extended period of time, and there's going to be a recovery back to westerly. So it's not that the stratosphere is breaking up because it's springtime. This is a sudden stratospheric warming event, and this recovery is happening because we still have radiative cooling over the poles. But what's interesting, and what I want to show you, is let me go back to the CPC page. So, actually no, I'll just stay here.
This is sort of playing with fire if you're the stratospheric vortex, though. You don't want to do this a week before the equinox.
Oh yeah, it's going to be a really boring springtime in the stratosphere. So what we're looking at here is a time height cross section. So these are dates at the bottom. This dotted line represents today, and so everything on the other side of this dotted line is a forecast, everything on this side is an analysis. And what you're looking at is the 60-degree north zonal mean winds, but now instead of just at 10 hectopascals like we were looking at in those time series, we're looking at it at all levels. So you can see that at all levels, starting in January, we had westerlies like you would expect in the northern hemisphere wintertime. The strongest westerlies were in the upper stratosphere. But as we went through January into February, we saw the winds were disrupted, but not a lot. And then by the time we get to the beginning of February, we see at 10 hectopascals, we see the oranges show up. That means that's where the sudden stratospheric warming happened. And if you look at this zonal mean wind reversal happens first in the upper stratosphere, and then you can see this downward signature of those easterly winds going down to the tropopause level, which is at about this level. And then eventually in the forecast, that anomaly, those easterly winds, sort of move across the tropopause from the stratosphere into the troposphere. And what you can see is usually the way that we think about this is we think about this in the context of the Arctic oscillation. So if I go back to the CPC page, and go to the AO, somewhere in here. So the AO is the leading pattern of variability in the northern hemisphere, everywhere above or north of 20 degrees latitude. And essentially, if you were to take all the weather maps at 1,000 hectopascals and say, what is the type of variability in all the weather maps, and you picked out what that pattern looked like, that most variable pattern, this is what you would get. And basically what it's saying is, when you have higher pressure over the polar region, you'll have lower pressure in these orange regions, or vice versa. So it's just saying that these are opposite things happening in these locations. The actual pattern or the sign doesn't matter, but it's the type of variability. So this is at 1,000 hectopascals, but you can do the same thing at every level going up all the way to 10 hectopascals. And when you do that, I think it's this one, you can look at a forecast of that. And that's what this is. So everywhere we're calculating that AO, that Arctic oscillation pattern, at every height from 1,000 hectopascals, where it matches the map we just saw, all the way to 1 hectopascal. We're looking at it in that time height cross section again. And here what we're saying is that when we have a sudden stratospheric warming, we have a very negative AO, and in this case, when we calculate it, AO is really defined at 1,000 hectopascals. When it's not at 1,000 hectopascals, we call it the Northern Annular Mode Index. They're pretty much the same thing, but AO is reserved for the surface. But what we get is negative NAM, and that negative NAM is persistent in the stratosphere and eventually works its way down from the upper stratosphere to the lower stratosphere and then has that fingerprint on the tropospheric circulation. So when we were talking about right now, as we're looking in the forecast going from this week to next week, and we started seeing that shift where we have that big Arctic high building in northern Canada and Greenland. We have the shift in the storm track, so now we have our series of storms coming off the east coast. The storm track is shifting a little bit further south than where it normally is. That might be this signature that we're seeing in the forecast. Higher pressure over the polar regions, lower pressure on the equatorward side of the normal storm track. And so that's what we're seeing. And the last thing, I know it's just after 1 o'clock, the last thing that I want to show you is that we can actually look at the vortex in 3 dimensions. So this is, if you haven't been to Zach Lawrence's page, it's great. You should, stratobserve.com, it's great. Let's see, let's go back to the first forecast. Okay, so this is right as the sun's stratospheric warming was happening. We're looking at the vortex defined at various levels, going from the upper troposphere all the way into the upper stratosphere. And as we loop through this, we can actually see how the tropospheric portion and the stratospheric portion are connected. And what's interesting is, if you remember, we saw that the stratospheric vortex, the upper part was disrupted first and the signature came down with time. And we can actually see that in this animation. So I'll just end with this beautiful eye candy before you all go off for your weekend. Wow. So, but yeah, so there's going to be some implications. Cold air outbreaks usually happen, especially in the European countries after sudden stratospheric warming, and it's looking like that setup is happening. We can also get cold air outbreaks over North America. Over North America, when a sudden stratospheric warming is happening, we're sort of competing with the tropical convection in the MJO, so it's sort of which one is going to win. And maybe we'll have more to say about that next week. So.
That's
Good
awesome,
stuff.
Andrea. Is there, there must be a listing of when the stratospheric polar vortex breaks down too close to the equinox versus when it starts to break down early and can recover? I mean, what's the longest, what's the closest that's ever come to the equinox and still recovered? Do you happen to know that?
So I do know that there's been a couple dynamic final warmings that sort of get lumped into the sudden stratospheric warming group because they look so much like a midwinter sudden stratospheric
Okay,
warming.
okay.
So actually, let's see, I have it here. There's a compendium data set, and it lists, you can go look at, let's see, this table. So it lists all the SSWs from 1958 onward, and it tells you their date in the various reanalysis data sets, and whether or not it was, you know, El Nino, La Nina, or neutral year, what the QBO was. So this is all really relevant data. But there's a couple that are in, like this March 2000 happened on the 20th of March.
Wow.
And is included because it looked like a major midwinter warming, but
Yeah.
really it was the final warming that year.
Yeah. Okay, interesting. That's really interesting.
So yeah, I will end it there, but it's more of a, yeah, so when you see this cold air happening next week, where is it? Nope, I don't even know where I started. There, this page. So when you're thinking about this big blob of blue next week, you can think you have the sun stratospheric warming to think about.
Wow, that's really interesting. Thanks very much.